We tend to look at large language models, your favorite GPTs or Claudes, and see a fully automated engine. We ask a question, we get a response, and it feels like the machine is doing the work. Let's look closer at a standard workflow. Say you need help scheduling a meeting. You open a chatbot and enter your prompt. The model will gladly tell you exactly how to schedule it. It generates a perfect sequence of steps, drafting the email and suggesting times. But that is where it stops. It takes zero physical action on your device. The model lacks the system permissions to execute these steps. The human remains the primary execution layer. You are the one switching tabs, querying calendar availability, and pasting data into the prompt. This exposes the core limitation of standard chatbots. They excel at knowing, but they are entirely incapable of doing. Bridging that gap requires a completely different system architecture, the AI agent. To achieve actual computational autonomy, we have to stop treating the LLM as an endpoint. Instead, we wrap it in an orchestrating framework, like the open-source project OpenClaw, and use external tools to build a continuous loop of execution. Moving past the chatbot phase means abandoning the linear prompt and response model entirely in favor of a dynamic, autonomous execution architecture. An AI agent operates on entirely different logic. Rather than waiting for your next prompt, it drives itself forward using an agentic loop. A task arrives at the central agent node. Before querying the model, it accumulates context, pulling adjacent data blocks like system instructions and memory. The LLM evaluates this to reach a critical decision gate. It asks, do I need external data or a physical action to resolve this? If yes, the agent moves into the action phase, routing the request to an external tool to trigger a web search or local terminal command. Once that external tool executes, the system observes the result and retrieves the raw output data. That new output data doesn't just sit there. It is fed right back into the agent's original context window, expanding its available knowledge base. This three-step sequence of reasoning over data, acting on it, and observing the results is known as the react pattern. The engine doesn't stop after one cycle. It repeats this loop continuously, querying new tools and updating its context until it determines no further action is required. By strictly following this react loop, the architecture turns a static text generator into a dynamic, multi-step problem-solving engine. A prime example of this architecture in the wild is OpenClaw, a free open-source Node.js service that runs this react loop directly on your local machine. Managing the constant data flow of continuous agent execution requires strict organization, so OpenClaw relies on a hub-and-spoke model. This diagram illustrates the system's core processing hub, the gateway. It acts as the control plane, an always-on WebSocket server handling message routing and managing the state of multiple concurrent agent sessions. But a control plane needs inputs, and human users rarely communicate through a single, clean channel. Users send requests from disparate platforms like the Slack app, or Microsoft Teams, or even Apple iMessage. To solve this, the architecture introduces adapters. They ingest varying external message formats and strip them down, standardizing them into a single, uniform data packet. Once standardized, these clean packets flow directly into the central gateway for processing. Without this standardization layer acting as a buffer, the fragile React loop would quickly crash under the weight of unstructured, unpredictable external inputs. Below the gateway sits the execution layer. This is where the agent physically interacts with your hardware and external systems. By default, the agent has built-in capabilities to operate a web browser or execute commands directly in your terminal. To expand those base functions, the framework uses skills. These are individual markdown files containing exact step-by-step instructions to teach the agent specific workflows. You can load a skill for testing Docker container images or updating Google Calendar APIs. But there are thousands of these skills available, and loading every single instruction manual into the agent's default prompt poses an immediate architectural constraint. Passing that sheer volume of text with every request would instantly exhaust the LLM's context window. OpenClaw solves this with a strict optimization strategy. As shown here, the system avoids loading the full files. It only injects brief metadata tags describing the available skills, leaving the rest of the window empty. The LLM reads these lightweight tags and evaluates which workflow it needs. Once decided, the system performs on-demand retrieval, pulling the massive full-text markdown file into the context window only when it's time to execute. This dynamic, on-demand context assembly prevents the agent's working memory from being paralyzed, allowing it to maintain access to a nearly infinite library of capabilities. Connecting an autonomous engine directly to your local file system introduces severe operational risks. Giving a language model unfettered access to read directories and execute terminal commands means a misconfigured environment instantly becomes a powerful backdoor into your machine. The most critical threat vector for an AI agent is a vulnerability known as prompt injection. This occurs when an agent processes an untrusted external input, like a summarized web page or an incoming email, that contains hidden malicious instructions embedded within the text. Acting as the central reasoner, the LLM can ingest malicious data, misinterpret it as a legitimate command, and execute it via the local terminal. To mitigate this, agents require strict architectural boundaries, operating within heavily isolated, sandboxed execution environments. Additionally, any third-party markdown skills require rigorous code review before implementation, and all system credentials must be encrypted before being passed to the model. True computational autonomy inherently demands total systemic access. Because of that exact trade-off, rigid security protocols are the non-negotiable foundation of any production-grade agent framework. Large language models no longer function solely as conversational endpoints. They have evolved into central reasoning engines, capable of orchestrating complex, multi-step workflows. Whether you are deploying OpenClaw, building with LangGraph, or designing a custom internal system, the mechanics remain the same. This animated diagram shows the whole architecture in harmony, standardizing inputs, managing dynamic context, cycling through continuous React loops, and sandboxing the execution tools. A system with this level of reach requires immense operational discipline. An agent's capability is directly tied to the security and isolation of its deployment architecture. Achieving real utility means stepping away from the chat window. It requires embracing the rigid engineering necessary to orchestrate, isolate, and manage true computational agency.
Thank you. Share and subscribe to Learn AI for more AI insights.